Sanders Kleinfeld, and it's my pleasure to introduce Chris Bernhardt. Chris is a professor emeritus of mathematics at Fairfield University, where he taught math for over 30 years. He's the author of several books on topics at the intersection of mathematics, computer science, and physics, including Quantum Computing for Everyone and Turing's Vision, The Birth of Computer Science, both published by MIT Press. Chris is here today to talk about his new book, Beautiful Math, the surprisingly simple ideas behind the digital revolution and how we live, work, and communicate. Beautiful Math explores and elucidates research of two mathematicians who are pioneers in the field of computer science, Claude Shannon and Alan Turing, and how their groundbreaking work laid the foundations for key technological innovations of the digital age, from streaming and data encryption to machine learning and neural networks. We'll be doing some audience Q&A at the end of the talk, so if you're joining us on the live stream, please feel free to submit your questions. And with that, please join me in welcoming Chris Bernhardt.
Thank you. Thank you for inviting me here today. It's nice to meet in person rather than...
Definitely. Always great to have a great audience. So I'll kick things off with a confession. I watch a lot of streaming video. So as you mentioned in your book, just a few seconds of high-resolution video contains tens of billions of bits of information. And I was wondering if you could just walk us through the math behind how we encode and transmit all that huge volume of data.
Yeah, so the book is about mathematics. So mathematics, we do computations, but it's also a language. And the great theories of the 20th century, we had quantum mechanics, theory of relativity, they were written in that language, and they're very well known. But we also have, as you say, the work of Turing and the work of Claude Shannon. And really, the work of Claude Shannon, well, I'm sure he's known amongst, well, he's definitely known amongst people in signal processing engineering, but he's not more widely known amongst the general public. And he, as you say, did some, he wrote this paper in the late 40s in which he talked about sort of digital information. He talked about how you could compress digital information. And of course, that's really important for streaming. You need to compress it before you stream it. And the other thing is, how you error correct. And it's a remarkable paper because it published, say, in the late 40s. And of course, at that time, everything was analog. The telephones were analog. And then, of course, he went on and also published another paper talking about how you could convert analog to digital information. And so he sort of set the agenda for the next 50 years. And there's some really beautiful math there. It's really powerful math. And I don't think it's, it needs to be more widely known.
Yeah, I think the whole field of information theory is not something that has gotten the level of acclaim and attention that it deserves. So I'd love to chat a little bit more about some of the key principles behind that. Maybe let's start with something that you were just mentioning before, analog versus digital, because I think people have an intuitive sense of the difference, but I was wondering if you could elaborate a little bit more. What is analog and what is digital when we're talking about technology?
So well, digital, well, nowadays, practically everything is digital. It's in terms of zeros and ones. It's a discrete, you've got a discrete alphabet, a finite alphabet, and you have discrete things either on or off. Whereas analog, you've got a sort of continuously varying signal. So things like audio and video, when you're actually watching them, they're analog. So today we take our analog data, we convert it to digital data, and then we reconvert it back to analog data before we use it.
Yeah, so let's talk a little bit more about digital data, specifically like as it pertains to technologies like streaming. So I think people have a good sense that when we're talking about digital data, like you were saying, it's referring to zeros and ones. And I think it makes intuitive sense that that can represent binary data. So yes, no, true, false, on, off. how is ones and zeros able to represent video data, say, like all the information about the pixels that comprise the visuals that we see?
So, all right, so actually this really goes back to Fourier and Fourier analysis. So, I mean, Fourier was mathematician. Actually, he worked with Napoleon Bonaparte, and he believed that any periodic signal could be decomposed into sines and cosines. Once you got and sines and cosines with certain frequencies and amplitudes. And so once you've got, you can just read, if you could read off the actual amplitudes and frequencies, if you've got a finite number of them, then you can just send that digital information. So, and the other thing, of course, that's really important is that we're sort of humans are bandwidth limited. That we can only hear within a certain frequency. And this is important. So we can hear up to, if you're young, you can hear up to about 20 kilohertz. But so when we encode, we only need to encode a certain band of frequencies. And so we just extract the amplitudes and the frequencies. And we send that as a digital stream, a finite stream of numbers. Yeah.
It's amazing when you think about it. And you alluded to error correction earlier, and I think we all take it for granted nowadays when we download or stream video from the cloud somewhere, that the visuals we see on their screens are going to be identical to the originals. But when you think about it, it's really kind of miraculous, right? We're transmitting billions and billions of bits of information over huge distances, hundreds of thousands of miles. Can you talk a bit more about how information theory tells us how we're able to do those sort of transmissions with high fidelity?
Yeah, so actually I'm somewhat older than you. So when I went to university, when I was at university, we all had record players. So music was all analog then. With a record player, you had to carefully clean the record, get all the dust off it. If there was a scratch, I mean, that was it. You just couldn't listen to it. And then DVDs came. And it was remarkable that, that there were no, you didn't have to keep dust off it. There were no scratches or pops. And it was, absolutely remarkable for about, 5 years. And then you just got used to it. That's how the way things were. And so the same thing with streaming and error correcting. We're just so used to error correcting working. And of course, it's an amazing thing. I mean, it's Shannon's noisy channel theorem that says that you've got a noisy channel, you've got noise that's corrupting your stream. You can error correct it, and he says there's this sort of channel capacity that within a certain rate, you can correct it to be as accurate as you want. And it's a remarkable theorem, because in a noisy bar, what you do is if there's a lot of noise, you talk louder and then you repeat yourself. And of course, continuous repeating is a form of error correcting.
Right.
But if you continuously repeat, then the rate the information flows slows down. And of course, what Shannon showed was that it doesn't. There's this rate here, and you needn't go much below that rate. If you're just below that rate, you can transmit information as accurately as you want. It's an absolutely amazing theorem.
Yeah, it's like it blew my mind as I was reading just that, like, mathematically, you can pretty much guarantee that if you follow the noisy channel theorem, you can transmit large bits of amounts of data really faithfully. So it's really incredible. And I wanted to also harken back to something you were saying before about compression in the context of streaming. Because we're dealing with such huge amounts of data, the ability to transmit it as efficiently as possible is really critical when you're dealing with, even though a lot of us have very high bandwidth situations today, it still puts a lot of demand on it compared to text. Can you talk a bit more about the compression algorithms that folks like Shannon have developed to solve this problem?
Yeah, so actually, and this comes back to something else. So Shannon defined information. And so, we're in the information age. So Shannon gave this definition of information, and it's in terms of the probability of an event.
Right.
And so actually, maybe just look at an actually concrete example. So suppose I have a coin, and I toss it. I do this example in the book. Toss it 3 times, right? And if it comes up heads all 3 times, I write down a 0. The other possibilities, I write down a 1. So the probability of getting a 0 is going to be 1/8. The probability I write down a 1 is 7/8. So now, suppose I just repeat this 1,000 times. And so I'm sitting here, and I now have done this experiment, tossing coin 3 times. I've done the whole thing 1,000 times. So I've got this string of 0s and 1s that's 1,000. It's 1,000 digits long, and I want to convey it to you.
Right.
Okay. And so Shannon said, well, the amount of information in this string with 1,000 digits is, well, about 544 bits. And so, I mean, he says that what you can do is rewrite it as a string with just 544 bits. Okay, so I could redo it. So if it's now with 544 0s and 1s, I pass this note, shorter note, to you, and you can decompress it and get back my string, my original string of 1,000 0s and 1s exactly. So, I mean, when you first come across it, it seems amazing. And the other thing, well, I'll come back to the compression bit in a moment, but the other thing is that Shannon's using information in a way that's, well, he's defining it. It's a very simple definition, but it doesn't, well, it's based on what we mean by information, but it's, in everyday usage, information's often connected with meaning and so on. And so that's another thing as we go through the book, there's things like information, learning, intelligence, and we're using those words
colloquially, yeah. But also, there's a colloquial definition and a technical definition.
Exactly,
yeah.
and often they're not at all the same thing. But anyway, coming back to compression. So again, if you want to actually compress this 1,000 0s and 1s, there's this really elegant result due to Huffman. So I think that everybody ought to see Huffman coding at some point in their lives. It's such an elegant result. And I mean, Huffman discovered this while he was a student at MIT, actually, that his professor told the class that either they could, come up with an improved compression algorithm, or they could take the final exam. I don't think he thought that anyone would come up with a compression algorithm, but Huffman did, and he was known for it for the rest of his life. I think that he felt that some of his other work was more important, but everybody knows Huffman for Huffman coding.
I'm grateful to that professor then, because who knows what our history would have looked like if that one event hadn't happened that way. So he made a different choice.
Right. Actually, the professor was Fano, who was another great mathematician in information theory. Yeah.
That's awesome. So another way to manipulate data that you talk about in your book is encryption, where with compression, the goal, right, is to transmit the data as efficiently as possible by minimizing the number of bits used. With encryption, the goal is actually to obfuscate the data in transit so that it can't be intercepted by bad actors. So can you talk some about the algorithms used for encryption?
Well, I mean, part of the reason I did that is so in everyday encryption, we have public key encoding, and we have symmetric key encryption. So the public key encoding at the moment is most often RSA, which is involved in, based on the idea that it's easy to find large prime numbers, it's easy to multiply them together, but if you've got the composite number and you don't know what the primes are, it's hard to factor it. Now, and again, a lot of stuff in encryption is not mathematically proven, so we don't know that for a fact, but nobody's come up with a way of doing it until Peter Shaw in the 1990s came up with a quantum algorithm. This quantum algorithm would factor in polynomial time. So this, of course, worried people because there's a lot of a lot of data that's encrypted, that's been stolen or wiretapped. I assume the NSA and all these agencies have vast amounts of data they can't read. Now, if there could be a quantum computer that could, solve this problem in polynomial time, then all of that perhaps could be read. So at the moment, there's a plan to replace this public key encryption method using RSA with other ways of doing it that are still, classical ways of encryption, but aren't open to quantum attacks. So yeah, in the book, I briefly talk about RSA, and I briefly talk about AES, the symmetric code encryption. And the AES is not thought to be attackable by quantum computers, so that bit of it's safe.
That's very reassuring, and it's also reassuring to know that folks are looking into how to make our encryption mechanisms more resilient and robust so that they will be able to stave off advances in quantum computing.
Yeah, so I think that's well underway. Yeah.
So switching gears a little bit, I wanted to talk more about the topic of computation itself. I'll start really broadly and just pose a question to you. How is it possible that the electrical circuits inside of our computer chips can perform all the calculations that underlie the software applications that we use every day?
Yeah, no, that's again, that's an amazing result. And of course, it goes back to Turing. That with Turing, who was trying to solve some problem in logic, and he needed to define what an algorithm was. And so his definition of algorithm was in terms of what we now call a Turing machine. And it's just this really simple thing. You just have this long tape, or perhaps infinite tape, divided into little cells. On each cell, you have one letter or one letter or blank, so only finitely many cells can have letters in them. And then this machine, it just goes along. There's a head that can just read one cell at a time. And it can perhaps rewrite what's on the cell. And there's a series of instructions. And the instructions are, depends on what state the machine is. So the machine can be in a finite number of states. So it reads off the state the machine's in, what it's reading off that particular cell. And then that's the only two bits of information it takes. Then it tells you what direction that head should move in next. It moves one to the right or one to the left. What to rewrite on the tape, and what state to enter next. So that's it. That's all really that comprises a Turing machine. And Turing said that any algorithm, this is his definition, any algorithm can, a Turing machine can perform any algorithm. And so algorithms at their most fundamental level are very, very simple things. I mean, so all you need is sort of switches and so it's very simple at the fundamental level. And I think that's something that when we talk about sort of machine learning again, there's a lot of stuff in the press that sort of I think is a little worrying when it talks about, they say we don't know how it's doing it and so on. Well, computers perform algorithms, and algorithms at their most fundamental level are very, very simple things. So we do know how it's doing it, but we might not know why it chose those particular parameters. But there's a process here. There's an algorithm.
Yeah, I think it demystifies it a little bit, right? If you can break it down to the underlying concepts and mechanics of how computation works, whether it's a machine learning algorithm or a fully human-designed algorithm, it's really using those same principles that Turing outlined for his machine, correct?
Right. Yeah.
Yeah, so I think for me, what was really amazing is just to think that a Turing machine can implement any algorithm. And there was this great meta moment in your book, I think, where you're talking about, like, you can implement a Turing machine with a Turing machine. So.
Right. Well, that's the idea of universal computation. Yeah,
right.
Yeah. So everybody knows that nowadays. You only need sort of one computer, and it can run any program you want on it. You don't need a program for doing this type of thing, a computer for doing this type of work, and another computer for doing this other type of work. So we have this one universal computer. And again, that goes back to Turing, and of course, again, that was a paper, before the Second World War, and so I mean, you look at these papers that were published really early on. There was Shannon's paper and Turing's paper. Shannon's paper was immediately recognized as being, really important. As I say, it set the agenda for the next 50 years. Turing's paper was a paper in logic. There were no computers then, and it was only after computers were built that people realized that here was the fundamental theory of computing in this paper.
Yeah, and today we take it for granted that our laptop, we can open it up and we can use it to do email or play a game or edit a spreadsheet. But if you do think about it from the perspective of, I guess, like 80 years ago or whatever, it was a situation back then where people assumed there were different machines needed for each of those different tasks.
Right. Yeah. So, I mean, at the beginning of the war, I mean, the most powerful computer was an analog computer, the differential analyzer that Vannevar Bush, again, well, he was connected with MIT, at MIT. And it was a machine for solving differential equations.
I believe, if I recall correctly, that machine was enormous and weighed something like 2 tons. Was that correct? Did I get that number right?
I forget how much it weighed. It may weighed even more than that. It's an enormous machine. A lot of these machines were enormous, yeah.
It's in the book, so check it out and fact check me if I'm wrong on that. So we were talking a bit earlier about machine learning, and I wanted to delve into it. Obviously, AI is a pretty big topic right now. So we've discussed through the Turing machine how humans can design and implement algorithms to solve problems. But the whole premise behind machine learning is that computers, when provided with the relevant data, can learn those algorithms themselves. Can you walk us through how that works at a conceptual level?
See, now I wouldn't say that they're I wouldn't say they're learning algorithms. So we now have so the example I sort of outline in the book is recognizing it's a vision problem, recognizing digits. Mm-hmm. So where we present a whole bunch of hand-drawn digits and get the neural network to learn and to say which digits it's being presented with. And so I wouldn't say that it was learning an algorithm. It's sort of really pattern recognition.
Right.
That we have this neural network with if you like, lots of nodes, and they're connected with these parameters that we vary until we get a good fit. But besides the neural network, we have some function that we're trying to optimize. When it outputs something, we want to know how good it is. So we're trying to optimize something. And so, associated with the actual sort of graphical thing with, looks like a tree, you have a function that you're using a numerical method of optimization. So when we learn something, we go to school and learn how to say learn multiplication. And we have this sort of rote thing. We have to practice with it, and we eventually learn it. And then we also learn to ride bicycles and recognize faces. And that seems to be a different type of learning. And we're not sure how we learn to recognize faces. And it's certainly based on our brains, of course, and neurons. But when we're working with neural networks, it seems strange to say that a computer's learned how to add. We just program. It's just an algorithm. But somehow we say, I think this is a game where we're using words in a little worrying way. That we're saying that it's learning, this neural network's learning how to fit the data. Well, there's an algorithm there. We're running this algorithm, and it's a numerical technique that's trying to optimize a function. So, yeah, that's what I think. Yeah.
I think, yeah, you're right, definitely, that sometimes our language tends to use terms that anthropomorphize what's happening, when in reality, the machine isn't learning the same way we think of learning. But I think at the same time, you were hitting on something really interesting here, which is that if we were to try to program a computer ourselves to recognize an image of a digit from 0 to 9, we wouldn't really know how to give explicit instructions to do so. But and ourselves, right, we sort of learn by examples, like, that's a 0, there's a little bit of a tail there, that's definitely a 6.
Right,
things like that.
Right.
Yeah.
Yeah. But this anthropomorphizing, I think, is a dangerous thing. So there's the ELIZA effect, where there was a program written in the 60s designed to be like a simple, it was a little chatbot, simple sort of psychoanalyzer that you'd ask it a question and it would respond, you'd say something like, "What's the meaning of life?" And it would say, "Why do you want to know what's the meaning of life?" And it's a simple little thing, but people would spend hours and hours and hours playing with it, and now I think so the ELIZA effect is giving sort of human qualities to our machines that they don't really have, and I think that's a real problem. Certainly as these large language models become more and more powerful, I think it's going to be more of a problem.
I think that's a really important and excellent point, that those large models are still effectively pattern matching algorithms. So you're providing some text, it's doing some pattern matching and providing some output text.
Right.
And I think that's like a really great way to think about it.
Right. And so, yeah, so the book's meant to be sort of an introduction to these ideas for a general audience. So the little neural network I have where I go through in detail, I think it's only got 4 nodes. It's not a practical thing. It's So I tried to give the simplest example I can that I think will illustrate the idea. And so that's what I've done throughout the book.
Yeah, and I think it's also probably important to point out, as you do in the book, that the neural network structures were developed because computer scientists, were looking to mimic some of the ways that our human brains interact with data. I should repeat myself. So, the human brain has structures like neurons and synapses and axons, and those connections enable us to process information, and that is what we are trying to replicate with neural networks to some degree.
Right, so certainly Walter and Pitts, were the originators of the idea, and they were trying to model brains, and so the idea of a neural network's been around for some time. So Walter and McCulloch and Pitts really sort of originated the idea, and they showed that you could do some computations that with it. And then there was another Rosenblatt in the 60s, I think it was, tried to get it working again. But really, we need a fair amount of computing power. So it's only recently that the idea has really been able to take off. We've got a large amount of computing power now.
Yeah, it's really fascinating how the results of all of these advances that we've made in the past have been able to come to fruition with the development of the computing resources necessary to do it at that kind of scale. Right.
And I think these large language models have surprised everybody, including the people who are writing them. Suddenly how powerful they became and how impressive they are.
Definitely. So I'd love to open this great conversation up to some of our audience questions. If you're in the room and you'd like to ask a question, please come up to the mic, and we also have some online questions as well. Why don't I start with an online question from Samuel. what do you think ugly math would be like? And that's a reference to, obviously, your title, Beautiful Math. And do you have examples? Can there be math that's so ugly, and that's why it's beautiful?
It's an interesting question. I think there's ranges of beauty. I mean, it's like any art form. I don't know if there's really ugly art, but there are certainly beautiful things. And when you look at, as I say, something like Huffman's coding, it's a really elegant, beautiful piece of mathematics. I think at times you see something and you say, oh, this is kind of ugly, but then it sort of says, well, this needs to be, you need to do something to it. It needs to be, it needs to be improved. So could there be something that's so ugly it's beautiful? I don't know. I'd have to think about that.
Yeah, it's a tricky one. Go ahead, question.
Oh.
Hi, sure, thanks. At the end there, you made reference to, LLMs and people not really understanding, like being amazed at what they could do. And I was thinking about Douglas Hofstadter's book, Gödel, Escher, and Bach, which I can only pretend to understand. But one of the things that I took away from it was the idea that there are levels of computation that we can't possibly understand. And just like we can't really understand the brain. Now, I may have misunderstood that, but I'm just curious what your thoughts are on that kind of speculation.
Well, certainly there are things that we don't know, and things, I suppose. So, in Gödel, Escher, and Bach, I mean, I think there's the idea of Gödel's theorem and so on, that here, I mean, what Gödel's theorem says is that if you have, and it goes back to the beginning of the 19th century when Hilbert wanted all of mathematics to be formalized. He wanted you to have a set of axioms, clearly defined system of logic, and you took the axioms, applied the logic, and you derived theorems. And he hoped that all of mathematics, well, certainly, it was beginning with number theory. All of number theory could be done that way. And Gödel, of course, showed that no, that given any formal system like that, there are always going to be statements that you can neither prove nor disprove. And so, there's always going to be stuff that we can't access, with our machines, yes.
Okay, thanks.
We'll go to another online question. Could you recommend some popular books, in addition to Beautiful Math, of course, that delve into mathematical concepts like Fourier series or limits, while also providing practical, real-world examples of their applications, such as how integrals are used in everyday life?
All right, well, let's see. Fourier series, well, actually, in the appendix of my book, I did put an appendix on the fast Fourier transform. So, I mean, that is something that we really need. I mean, you need to go from our analog data to our digital data. We need to use a Fourier transform. So the fast Fourier transform is something that is incredibly important. And so I did put it in the book, but it's sort of, it's an appendix because it is a little bit more mathematically sophisticated. So Fourier series, the trouble is mathematics is a hierarchical subject, and it depends on how much mathematics you know. So my other book, another book was Quantum Computing for Everyone. And that I tried to keep the mathematics down to a minimum. So, there are no eigenvectors, eigenvalues in it. I didn't use complex numbers. And you really don't need that until you get up to sort of quantum algorithms. And if you want to try and look at Shor's algorithm, then perhaps you need it. But you don't need it for that. But people complain, say, well, why didn't you write it using complex analysis? And so there's a level, I mean, depends on your background. I mean, there's a book called something like Mathematics. A mathematician reads the newspaper, which is an elementary book, but it's a good book. Yeah.
Yeah, thank you for those great suggestions. I think your book as well does a really wonderful job at making the mathematical concepts approachable to people with different levels of math background. It's definitely a hard balance to strike, and I thought you did really great with that.
Thank you. No, it's meant to be an elementary book. Yeah, of course. Yeah.
So we have another question here. How do you think AI will impact the field of mathematics in the future?
That's well. So I don't know. So I'm writing another book with a friend of mine, and where AI is incredibly useful is for programming. That in writing this book, we're using LaTeX, and we draw the pictures in something called TIXI. And I use this stuff so infrequently that I can never remember what the syntax is, what the command is. And here, with an LLM, you just say, give me the TIXI code for this. And it won't be quite what you want, but the code's there, you modify it slightly, and you're away. So it's it's really useful. So in terms of AI, that there's AI from the beginning. There was Turing with his Turing test, and von Neumann with the singularity, saying computers are going to reach the level of intelligence where they'd exceed us, and they'd be designed better computers. We'd lose any idea of what was going on in intelligence. They'd just be so far in advance of us. So that's one stream. But there's another stream with Vannevar Bush and Licklider talking more about augmented intelligence. So Licklider talked about this idea of man-computer symbiosis. And that, to me, seems to be, so at the moment, much more the direction we're heading. That, when I work with a large language model on something, I find it a really useful assistant. But I don't worry about it becoming my overlord. It's not going to take charge of me or anything. It's a really useful assistant. So I think I see that augmented intelligence. I think that we, in conjunction with our computers, are going to become more intelligent. So that's, at least I hope I'm right. That seems to be the direction I'd like to see things go. Yeah.
Yeah, I think we've only really scratched the surface of the ways that we can collaborate with AI models and the productivity that can provide. So it's really exciting and inspiring to think of what our future could look like.
Right, yeah.
We have another question here. Let's go to one in person.
So I have a kind of like a follow-up to your last comment. So you started, or rather, while you were talking, you mentioned talk about the Turing machine and then the quantum algorithm, and we hear all about the quantum computer right now. So I would like to hear your thoughts about AGI and how, not necessarily objectively how far we are, but what are your thoughts around achieving AGI?
AGI. Well, I don't know. I don't know what the definition of AGI is really. I think we need to have some clear definition of what we mean by it. I mean, it's sort of, Turing started off with a Turing test that was going to measure whether a computer could be intelligent. And I think we will probably say now that that test has been met. AGI, I don't know. I don't know what the test is for AGI.
We should probably define that acronym for audience who aren't familiar with it. It's artificial general intelligence, correct?
Right, correct, yeah.
Thank you.
So switching gears, we have another online question as well. Can we assume we are observing uncompressed information from the natural world? Or do we observe some form of compressed data above the quantum realm? Curious if there's a larger data layer hiding somewhere in the quantum realm.
That's a tough question.
A bit of a thought experiment, huh?
But of course, everything, we're limited by, our senses. We're limited by what we can see with our eyes and what we can see with our ears. So, and we we have machines that sort of convert things so we can extend our senses. But yeah, you've got to believe there's a lot of stuff that we'll never be able to access, a lot of stuff out there. Is there a, I don't know, a larger data layer hiding somewhere in the quantum realm. Yeah, I mean, the quantum realm is such a weird realm. Yeah, so I think I'm going to pass on that question.
To be determined.
Right.
So any other questions in person? If not, I had sort of one final question for you, which was, in the process of writing this book, what were your main takeaways? What did you learn from the experience of writing this book? And if you had one takeaway to share with the group, what would it be?
I think when writing a book, you hope there's going to be some sort of story that runs through at least part of it. That a lot of these areas are taught separately. There's you'll take a course in this and a course in that, but you feel that there should be some sort of way of some sort of story that runs through it all. And I think, to a certain extent, I saw that more clearly, and I hope I've expressed that in the book.
Yeah, I think that definitely came across. As humans, we do learn through narrative, and learning how all this came to be through the biographical details that you also include about Shannon and Turing and the experiments that other folks at that time were coming up with. We really get to see a perspective on all of this stuff, which is really amazing. Right.
Yeah. Of course, also in the book, I include stuff about the telegraph and stuff that came before, because a lot of the underlying problems, are quite old, and people wanted to solve these things for some time. And of course, now information, part of it is that it's so quick, and I mean that really changed with the telegraph. That before that, information was a much slower process. And I illustrate that with a couple of examples in the book with the arrest and hanging of Table.
Yeah, but I think to the point you just made, it's really fascinating that the same challenges that plagued the telegraph are still the underlying challenges today with streaming. We've just figured out how to solve them through things like the noisy channel theorem and also increased computing resources.
Right.
But there's a really amazing through line. People don't think about the telegraph when they're watching Netflix, but it's the same general principle that's underlying how you're getting that data pushed to you, which is really incredible.
Yeah. And again, there was sort of this, there was a telegraph, which of course was digital, and then suddenly everything went analog. So it's a very interesting story. Yeah.
And a back and forth too.
Yeah.
Well, thank you so much, Chris, for joining us today for this really insightful, fascinating conversation. Chris's book, Beautiful Math, is now available in bookstores and Google Play if you like ebooks, wherever you get your books. So we will hope you all check it out. And thank you so much for joining us at Talks at Google today, Chris.
Oh, thank you for inviting me. Thank you for being here.